Swayam Prabha. Digital India. Educated India.
Welcome to covalent bonding, everybody. Let's look at what covalent bonding is all about according to the covalent bond theories. There's just really two theories. There's the valence bond theory, and then there's the molecular orbital theory, which is really based on mathematical calculations. Let's look at bonding in general. What do we mean what type of bonding are there? Let's explore that. There are three basic types of bonding. One is between metals and metals. The other one is between metals, the blue, and the non-metals, the pink box. And the other one is between the non-metal and the non-metal. Now, everybody, you all know that we have a very, very important staircase on the periodic table. That's something that you need to know. Anything above the staircase is a non-metal, below it is a metal. Right? So the metals and the non-metals have their own regions. The only time that they come together is when they make crystals, ionic bonds. So the metals throw their electrons and become a positive. The non-metals catch that electron and become negative. And it could be any number of, it doesn't have to be 1 to 1. I'm just showing an example. And then they stack up because the attractions are spherical. So let's say this is your metal and here's your non-metal, plus minus. Now these can attract in all directions. So here's your metal and your non-metal. So metal, non-metal, and then another layer of this, that would be a unit. And you'll have millions of these units going in 360 directions, stacking up. So it's a crystal lattice. So all of these get stacked up with this metal, non-metal units, right? That's ionic bonding, and most of the Earth's crust that you stand on is made out of very strong bonding. Lots of ionic bonding in there. Ionic bonding, in lots of the crystalline stuff that you get, stalactites, stalagmites, and so on. So ionic bonding is kind of most of the inorganic stuff is ionic bonding. Now, you can take, so here, as we said before, you're going to have these stacked up crystalline forms, and these can go on forever. Really, they're only limited by space constraints. There's really no limitation to how far they can go as long as you have space and you have ions. They can grow and grow and grow and grow and become huge lattices. That's ionic bonding, right? Then we have another type of bonding where you don't have any non-metals, we just have metals, and the metals then exchange electrons and throw these electrons around. Let's say you have a nickel metal, it throws its electrons around, becomes positive, and it can become 2 plus, 3 plus, whatever. And all these electrons are going to then run around that metal. And let's say your electrons get thrown out, and they're going to be running around all over these metals, gluing them together. At least that's the theory. So that you can make them into, you can bend them, you can, they're going to be malleable, ductile, wires, sheets, and so on. Here's an example. So that's just metallic bond, just pure metal. Just usually, if it's copper wire, it's all copper. If it's silver, it's all silver. So that's metallic bonding. All right, let's look at the third one, and probably the most important one, because all life forms have to have this kind of covalent bonding. Not just life forms, but even the atmosphere, oxygen, nitrogen, they have to have covalent bonding. Okay, so let's hear what happens is you are going to take a covalent atom, and then another covalent atom. Let's say you have hydrogen. When it comes to bonding, hydrogen behaves like this group because it needs an electron for octet. So let's say you have a hydrogen atom with an electron. It meets another hydrogen atom with an electron, and they say, hi, how are you? Exchange electrons and become friends forever. So that's pretty much covalent theory right there. So valence electrons are shared in covalent bonding. Now, does this happen instantly? How does it happen? How do you know, where it stops? Let's take, for example, two hydrogen atoms. They're at a party, they're like all over the place. And then suddenly they notice each other. She looks good. And they start getting closer. So then attractions form, attractions between the positive nucleus of this atom and the electron of this hydrogen. The dot in the center is supposed to represent the positive, and the whole balloon is a squishy electron cloud, you can say. Now, electron clouds won't have such a defined boundary. In theory, the electrons can go on forever. Okay, they kind of, but then most of the electrons, 95% would be here. We call that an orbital. So these electrons, when they get attracted, they get closer and closer, and they get really, really chummy. And then because they get closer, they relax, and they get lower and lower in energy, and it's getting more and more exciting. Before then, you know it, they're bedded and bonded, and there forever. Okay, that's the stable place. That's where they're happy. So they kind of tie the knot and they are bonded. That's a bond. That's a covalent bond. So there's an electron attracting, the proton is attracting this electron, and this proton is attracting this electron, and it happens at a certain distance, and they're happy here. All right. Now, that distance, there has to be maintained for a good relationship. And if they get too close and they get into each other's space, the protons and the protons start repelling and gets really hot in there. Time to call the marriage counselor. This is where you got to stay to have a good relationship. So that's your bond length. And the amount of energy that you lost going over there is called the bond energy. So bond length and bond energy is at the minima. That's when they have a good, stable relationship. Stability, that's what they're looking for. Don't get too close, and if you don't get too far apart, just stay right here where you have a very nice, stable relationship and bond. That's covalent bond for you. Okay, so let's look at that. So here, let's say this is when they were atoms. They were like far apart, and so there's really no attraction. Let's say that's the 0 point. Then they get closer and closer, and at this point, they have a very nice distance where they're actually coming together and having a bond. Even though it's like that, it's more like this. And the distance between the two nuclei here and here, the average of all of that is the bond distance, which is right here. So whatever that is. So if this is a hydrogen atom, the bond distance here, that's called the bond length, is going to be, so this is your bond length. And this would be different for different atoms. If this wasn't hydrogen and this was, let's say, chlorine, you'd have a longer bond length. This would happen here, not here. This is probably the shortest bond length of all, because hydrogen is the smallest atom. So this is 0.74 angstroms. And how do we know that? All from X-ray measurements. And the amount of energy that it gave off, because it's getting more and more stable in this relationship, and so that's the stability, energy of stabilization, that's lost. So that is called the bond energy. And if this is hydrogen, this is going to be 104 kilojoules per mole, and that would be the bond energy that's lost. Okay, that's bond energy, and minus delta E, that's bond energy, 104 kilojoules per mole. So the bonding energy is a measure of the stability, the fidelity, or the stability of this bond. So here we're going to have a very nice curve every time you have a bonding. Let's say you have a stronger bond with different elements, then you're going to have a lot more energy being released. Like if you have a double bond, it's going to come down even more. A triple bond will be even more. So, and also there is also a correlation between the bond, when the bond length gets shorter, the bond energy that's released also increases. So you want to get very deep in this well if you want to have a good relationship and lose a lot of energy and get stable. Now this is all valence bond theory. Valence electrons are shared to obtain an octet. In the hydrogen's case, it's actually 2 electrons, and that is called the valence bond theory. So in a nutshell, that's what it is. There's a lot more to it, but just a simplified version of that. When the hydrogens come together and they're at this really nice, beautiful spot in their relationship, we have a very nice distance. The distance between the center of this and the center of this, that's called the bond length. If you get too close, then familiarity breeds contempt, and you're not going to be too happy, and the positives are going to repel, the negatives are going to repel, and you're going to be screaming down to your most stable, happy place. That's your bond energy, bond length. So the bond length that's the distance between the center of this atom and the center of that atom, and it's averaged over many, many, many atoms to give you this length. This is for hydrogen. For each element, they would have a different distance. So that is going to be your bond length, and the energy that you lose is going to be the bond strength, the bond energy, which is a measure of the bond strength. All right? Okay, so that's a very simplified version of covalent bonding. All right, guys, so see you next time. Bye.